So today I'm going to share our experience building Cozystack as a platform framework, actually platform. But first, a few words about me. I started my Kubernetes experience working for Vedas. I was automating hundreds of servers. That was a really interesting experience. So I bring storage and Pixie automation there. Then I switched to work for Pelark. We were developing Deckhouse Kubernetes platform, where I introduced virtualization, and since 2023 I founded Enix, and for now we do open source platform for ISPs and other people to provide managed services, just like in AWS but for on-prem installations. Today I'm going to tell you about two things. The first is a platform approach. Why is it needed for? How it is working and how can you build your own platform, which solutions you can consider, and why we choose Kubernetes as a main solution for building our platform. And the second topic is more deep about Kubernetes Aggregation API Layer. That's another kind of technology which allows you to extend the Kubernetes. I'll explain you how it works, the various options to extend the Kubernetes, and how we use that in a real world. So let's start from the platform approach and let's talk about what the platform is. Let's say you have some customer and you have some customers, and all of them need to run their own applications. The customer one have application which depends on such services like infrastructure services, Kubernetes, Redis, Postgres, S3 buckets, Kafka, ClickHouse, for example. The second customer has another application. It depends on some other services which are not exactly the same but slightly different. And the customer three also have their own set of services. So we decided to build our own solution for all of them and to pack them all together into platform and ship as a union box solution. But before you start provisioning those services, you also have to take care about your infrastructure part, actually about the storage, service provisioning, networking, virtualization, how you're going to monitor it and manage this. And you as a user, if you're working on higher level, we can say application layer, if you will consider to build such stack by your own, you can try to do that. Actually, you will start building first infrastructure stack, then platform stack, then only in the last part you will run your application. If you have no enough experience, you will find that you need to know really wide spectrum of technologies. You need to have expert in all of them. And you also find that those technologies have bugs, and you also need to support this stack. So finally, it can be broken and you'll be unhappy. So how can you secure yourself from that? You can actually try to offload this stack to using ready as a service pattern. But what does it mean as a service? Here is a nice chart which explains you your maintaining support for each part of the your infrastructure. If you're going to support, if you're running on site, it might be very difficult because you need to take care about almost everything, start from server provisioning, storage, networking, and you also take care about your application you're going to deploy. If you go and use some infrastructure as a service solutions, let's say some cloud platforms, you can be secured for, you can offload the virtualization, servers management, storage and networking, and just operate with virtual machines. But you still have to worry about operating system management and running infrastructure services. The PaaS solves that. So you just need to take care about your application deployment, and you can use ready infrastructure services to provide it as a service. There is also a fourth funny option. It's called SaaS. So you can actually do nothing and just use ready products like Google Drive or Gmail or Slack. That's all of this is software as a service. But since we do platform for our clients, we want to provide the almost ready stack for them, infrastructure stack that they can just consume and use. So we decided to go and provide this layer. The customer actually works only on the top things, and that's only the thing they have to worry about. The rest thing is covered by our platform and by our support. But how can you build your platform and which solution to use? There are many of them. You can consider really default one is OpenStack, but when you're trying to adopt OpenStack, you find that it is very difficult to support, and it has a lot of asynchronous APIs, and you actually need to have separate development team which will take care only about the OpenStack and all of its parts. The other option you can consider is using Docker. Docker provides you really rich library of existing software which you can just run as Docker run something. And it works pretty well, but the problem of Docker is that it works just on a single node and it does not support normal clusterization. There are also nice solution, Cloud Foundry. It was very popular before Kubernetes started to be being popular. For now, I don't see many companies who are actually using it. And finally, Kubernetes, which is very standardized and it has a lot of things inside. So Kubernetes nowadays is standardized solution for run server workloads and infrastructure services. It implements modern software patterns. That means if you have virtual machine, you don't have to worry about how it will be properly reconciled. Anytime Kubernetes will handle full lifecycle management for it, it will migrate it in case of node failure. It has really nice RESTful API, and it is easy to extend. It has a lot of ready operators for everything. So here are operators we use in Cozystack. You can see also KubeVirt here, which is also kind of operator for virtual machines. Kubernetes implements such option that you can extend it with custom entities and have operators which are managing full lifecycle for your applications. Okay, Kubernetes is good, but Kubernetes is so different. Many different companies write various operators in different languages. All of them have a very different spec. So for now, on the screen, you can see various database objects. This one for MariaDB, for Kafka, for ClickHouse, and for Postgres. They are totally different. It's difficult to control them, and you can't actually create some unified API or UI for them. But with great power comes a great responsibility. How can you control those operators? Because they are not uniform, they have no UI, they're difficult to extend. If you want to change something, it's very difficult to change operator itself. And it is difficult to control. That means if you provide your users custom resources for your operators, you have to worry about some specific fields which they can use. For example, they can replace image for custom resource, or use really higher resources and compromise the system actually itself. We don't want that. What kind of solutions do we have here? We can write policy, but if you write policy, it will solve just part of the problems. You can restrict users to change some specific fields in your custom resources, but it is also very difficult to control. Another option is to create API and write operator for operators. But difficulty level is infinity because you need to create custom resources for any type of resource, and it is very difficult to extend and support. You can also use Helm charts, which are pretty fine here. They always have the same interface, values file, but problem that Helm have no full lifecycle management. Yes, it can put some YAMLs into Kubernetes, but it will not guarantee you that some Postgres replica will be properly fixed in case of node failure. So we have to use operators in backend anyway. Our approach is hybrid. So we decided to use Helm as API. User can write their own values and deploy charts into Kubernetes, but this chart will deploy actually some kinds for operators. So actually this kind is managed by operator, and this way we have interface for configuration. We specify only specific fields we want user to change, and we still have full lifecycle management by the operator. In fact, this is changed to FluxCD. So we can, FluxCD is kind of Helm operator for Kubernetes, and it allows you to specify some kind Helm release which will develop deploy the rest things. If user wants to deploy something, let's say virtual machine, it also creates Helm release, which then creates virtual machine managed by KubeVirt. If user wants to deploy Kafka, it creates Helm release, which creates Kafka resource, which will be managed by Kafka Streams operator. This is how it works, but this is how it looks like. So we can see that those resources have same kind. They have different chart in their specification and some repository where they get installed from. We actually run our HTTP server right in Kubernetes, so it stores the charts for all the applications we serve to. And the values for them are quite similar. It's very different to the example I showed you before. So we can show them in dashboard, and that works fine. Every Helm chart here can also be with icon. It can have definition, description, and some additional default things which you can organize such way. In fact, if you want to deploy any application, you can create single YAML file in Kubernetes and it will deploy. The parameters in this YAML can also be rendered in dashboard because they comes with OpenAPI spec, and this OpenAPI spec can be shown as just graphical parameters. So finally, we decided to use Helm charts to define applications, use operators to managing application lifecycle, and use KubeApps. Our dashboard is based on KubeApps project for rendering and showing UI interface. That was working really fine because our generic case is some internet service provider who use Cozystack to provide ready backend for their services. They usually have some middleware, let's say website or billing system, which ordering those services in Cozystack. So we have some kind of single tenant system. Their billing system is only user to Cozystack itself. Problem comes when you're trying to organize multi-user access to Cozystack, because we got this request and we start supporting those cases. Users want to have direct access to Cozystack to provide multi-user access, and we need to organize it somehow. And we face with the problem that you can't just give them access to your management cluster because everything is Helm releases. Despite the fact they're deploying different charts, they're still having the same kind. And when you restrict your users using Rebug model, you can't restrict such things like listing and creating only virtual machines, but not allow them to create Postgres, for example. But we want to have such opportunity. So in fact, we decided to create our own custom resources. Let's say custom resources for now, because they're not exactly custom resources. But since you have these custom resources, for now you can create a Rebug role that will allow you to create Postgres, but not allow to create virtual machine. That works fine. The only problem that you need somehow to sync the state between these resources and these resources. The default way is to create some kind of controller or operator, which will take those resources as storage and move them, create actually Helm releases. Other problems we have here, we create another state, and that means that something can go wrong. We don't like to complicate the system. And it works only in one way. So if you change Helm release here, the changes will not be reflected in our specific API objects. So another option is to use API server, which will use Helm releases in Kubernetes cluster as storage objects, and it will create such resources in dynamic way. They can be created really dynamically, and they will be existing only at the time when you're querying such resources. Such scheme is stateless, so if you change, and it works in both ways. If you change anything here, it will be reflected here, and if you change something here, it also will be reflected here. Now let's talk about the implementation of such pattern. And for making this, you can use aggregation API layer technology in Kubernetes, which is another way how can you extend the Kubernetes. So let's talk about the ways how can you extend the Kubernetes itself. Imagine we have Kubernetes API server, and when you have Kubernetes API server, it always stores the data in etcd. This API server has some objects like pods, nodes, and it have different API groups. For example, deployment stateful sets, they are in API group apps. So all of these resources are managed by Kubernetes controller manager. And you can also extend the Kubernetes by creating custom resource definition. So you define that this cluster will have another set of resources, let's say, in API group, some operator, it will have a resource database, and we can run operator, which will actually do the reconciliation logic for these kind of resources. So it will move the real world state to desired state you specified in your resource. The same way KubeVirt works. It has registered another kind of resource in Kubernetes, and it has operator or controller who controls these resources. FluxCD works the same way. It has Helm releases, which are just ordinary resource in Kubernetes, and it controls it through the Helm controller. But if you know such thing like metric server, it works totally different. It also provides you some resources, but actually it is metric server. In Kubernetes API server, it registers just API group and says that all the requests to this group should go to the metric server. And this metric server also responds that it should serve pods and nodes, quite similar resources to the core one, but they're different. If you do any requests to those resources, metric server will go directly to kubelet and request the metrics from the kubelet itself. So we decided to use the same approach to implement our own API server. So we registered our group like apps.cozystack.io and implemented our own API server, which says that we have to serve databases, virtual machines, Kubernetes. But when you query those resources, the requests go directly to existing Kubernetes cluster. So when you query databases, it will query actually Helm releases and represent it a different way. This technology is called API Aggregation Layer, and I want to show why it can be useful, and you might be using it in how it works actually. You can see that there is no CRDs registered yet, but there are a lot of API resources in our API. All of them are served by this API server running in Kubernetes. How it works. In Kubernetes, you have such API services resource. When you create it, it will take a look for this service and send all the requests to it. And inside of this namespace, we have service, we have deployment, which is serving those requests. So there are actually two pods running and handling all the logic. When can you use aggregation API layer? There are a few options. For example, if you know Kubernetes can handle not only declarative resources but also imperative. For example, such commands, if you were using them, they're also using imperative logic. So you can exec into pod, you can see the logs, you can use port forward. But they're still handled by declarative objects if you define it as custom in resource role-based access control. You can restrict or allow creating logs, and that will restrict to seeing the logs of the actually to the user. This is usually done by the such technology like aggregation API layer. So when user sends the request to API server, it goes directly to kubelet, do some stuff, then send the feedback back to the user. With aggregation API layer, you're not tied to use only etcd. You can use any backend you want to. So you can use Postgres, you can store the data in Prometheus or any other storage you want to. You can even implement your own storage if you want to. And there is also such pattern as one-time resources in Kubernetes, which you can't list, but you can create. For example, this command, kubectl auth, it generates the request, like it creates resource self-subject access review, and API server responds back with additional information here in status. With API server, you have full control over conversion, validation, and output formatting. So you can send any requests, they can be modified by API server, and you can actually render the table to the user how it will look like. There's few anti-patterns why you should not use aggregation API layer. And the main pattern is when you have no stable backend and where you have slow requests in your backend, it's better to not use aggregation API layer. That means if you go to your Kubernetes API server, you actually expect that you will get immediate response from it. But if it depends on dedicated storage, which is not accessible for some reason, you will get some strange errors from the Kubernetes API, which you don't expect to get. To solve this, it's always better to use controller pattern instead. That means that you have controller which taking care of your remote system, and it continuously responds the state to the API server. So your API server always have updated information about your objects, and user can always get the information about this, even if the system is not accessible. Our approach is different, so we decided to use this technology for create dynamic resource registration. This is something unusual, and I think nobody did that yet, because in Go world you usually get used to use code generation a lot, but we implemented it in pure Go, and that means that when you create requests to your API server, it can provide you dynamically generated resource type of objects, and then you can start work with them immediately. So you don't have to recompile your API server to add in other kinds. So purely dynamic API server written in Go, challenge accepted. How we did that? Before you start writing your own Kubernetes aggregation API server, you can consider these two projects. The API server builder, it's something like Kube builder for API server. Finally, you can find that it is alpha and it is kind of outdated. It is not very useful. You can also consider using sample API server, which shows you exact implementation of sample API server with etcd storage and modified. What we actually did, then we created common resource kind. We named it application. Then we implement our own registry. The default operator used etcd. We replace it with Kubernetes client, which allows you to go directly to the existing Kubernetes cluster and use it as a storage. Then we implemented configuration loading. So our API server reads this configuration file, which defines what which kinds should be translated to which releases. So for example, Postgres will be translated to Helm charts with such name with this repository, and they also have prefixes which also will be removed. And finally, the last problem is OpenAPI. Since you use Go, Go has internal logic for finding how can you provide OpenAPI spec for your resources, and it tries, and if you use single resource, this logic will be broken. You can test it with kubectl get in row OpenAPI spec. You'll see some output with specification for your applications. In fact, you can modify this using this post-processor spec. So if you want to modify it, we actually did that. It also extends it with all the custom types we're adding and reading from the configuration file. So what we've got in the end, user can create such resource. It will be automatically translated to Helm release. The name, the kind will be translated to this part, like chart name and the repository specification. The name will remove the prefix. Application version will specify Helm chart version, and the values are actually spec. The spec you specified, they will be fully translated to values. Virtual machine will look this way. So pretty similar. We have very similar resources for everything, even Kubernetes. So we use Helm charts, which defines all the needed YAML files to run Kubernetes inside of the Kubernetes. And this is how it looks like. So user can operate with such resources as kind Kubernetes. In fact, it will create FluxCD Helm release resource, which will then deploy the rest part, which is existing in this Helm chart. And everything without any external controllers. We decided to go forward and add additional unification. Let's say we have Kubernetes cluster, but we need to provide user additional feedback, like how can we show the secrets to accessing the cluster, actually to provide kubeconfig, users options to download their kubeconfig. We decided to implement such role. It is very custom role which allows you to show users exactly those resources they shown in the resources specified here. They shown in dashboard and can be easily downloaded. Another option to unify this, we also decided how can we show the status of every pods of Kubernetes for the user. Because again, every operator is different and they spawning pods different way, and we need some common way to showing this in dashboard. So we introduced workloads which have type and kind. They can be operational, and there is a list of replicas, the amount of replicas, how it consider it to be operational or not. And we introduced our own controller, which works exactly the same way like every service monitor, pod monitor. It selects the pod using selector. Yeah, it has type and kind, because different workloads in the same application can have different types. Let's say Redis can have Redis replicas and sentinels. Kubernetes can have control plane pods and also workers. So this resource always aware about the minimal amount of replicas should be running. Otherwise, the service will not be considered as operational. And here is selector, which allows you to select the pods in Kubernetes, and it will provide you the information. It will collect the information about the replicas actually. So we have one workload for control plane. The second one is for worker nodes. Since we run virtual machines right in Kubernetes, they're running the same way like pods, and we can use the same entity to collect information about those resources. This is how it looks like in CLI. So you can get workload monitor. You can see that they have name, kind, type, information about replicas. Worker node have no information about existing replicas, about replicas itself, because we use cluster autoscaling and we don't know which exactly number should be existing for the worker nodes. So one time we can see 10 nodes, one time we can see 2 nodes. This is how it looks like, and operational state. In fact, they generate another type of resources which called workloads. They have the same information like kind and type, but they also collect CPU and memory usage. And the state of the operational here means if the pod ready or not ready. Why do we need that? we decided to implement that in another controller, which taking a look for these resources and collects everything into Victoria Metrics storage. This is Prometheus compatible storage, which collects the information and implement billing API the same way. So we implemented billing API server exactly the same way. You can query Kubernetes API directly and get information about the resources consumption. Let's see how it looks like. Again, we have API resources in billing NX EO group, and we have kind usage report. We have registered API service in this group. And inside of this namespace, we have this service running, and there are pods which actually implement our billing API. The API server controller, which collects the data into Victoria Metrics, and the Victoria Metrics itself. And how user can work with this billing API? Anytime when they want to get information about some usage period, they can create usage report. They can even specify start timestamp and end timestamp and send this resource to Kubernetes. It will automatically go to Victoria Metrics, then go back to the user with the information about resources consumption. For example, you have eCPU hours, storage, ephemeral storage, and memory gigabytes. And this report is split by workload kind and type. So you can put different pricing for Postgres and for Kubernetes, for example. So anytime when your user want to get this request, they specify this query, and the report is return it in the same resource. This is one-time resource, which is not existing usually in Kubernetes, but it existing only in the time you create this request and you send it to billing API server. So conclusion, finally we get such unified resource which packed in Helm chart. You can easily extend this logic to another type of resources. This Helm chart includes custom resource, services, and some additional resources which can be used, and they are managed by operator, which provides you full lifecycle management. It knows how to manage the operation the best possible way. And we have our custom resources, which implements the better visibility for the user and provides you extensibility and unification. The same way we created a framework where you can define your application like parts of Helm charts and have common unified API for your users. So you can see that we have a lot of resources like ClickHouse, Nuts, Postgres, even CVDFS. They shown on dashboard the unified way. All of them have icon and description and definition, so user knows how to work with that, and it is always similar. And they have information about the running workloads. Let's say monitoring application, which holds almost everything which can be used for monitoring. It shows such output. Finally, I'm going to provide you a few links which can be useful. The link to our project, it is open source. You can find it on GitHub. Please give us a star. Lately, we get accepted to CNCF, so it might be also interesting to you because you can be secured from license changing, and we already have some community. Here is an article on Kubernetes.io where I describe how we organize this dynamic API server in Kubernetes and Cozystack, and a link to my previous presentation where I describe how we ship the system components and the platform itself. Many thanks to my wife who did this beautiful presentation, designed for it, and please leave your feedback